Okay, so the first comparison test that we're going to talk about is called the basic comparison test. And it says, suppose the series A sub n and the series B sub n are positive term series. If the series B sub n converges and all the terms of A sub n are less than or equal to the terms in B sub n for every positive integer, then the series A sub n must converge. So in other words, if you have a series that has smaller terms, then, well, it doesn't have to be smaller. It could be smaller or equal to the terms in a convergent series, then you know your series converges. Now, on the other hand, if the series B sub n diverges and your terms are equal to or greater than the terms in the divergent series for all values, then your series must diverge. So that kind of makes sense. It's like, okay, you've got a series that converges, so if this series is less than that series, then it must converge as well. If you got a series that diverges and this series is bigger than your series, then your series must diverge. Okay? So the hard part sometimes is figuring out, finding the right series. Okay, so here the series is 1 over 2 plus 5 to the n. Okay, now if n is greater than or equal to 1, then I know that this value is actually going to be less than this value, 1 over 5 to the n, because 2 plus 5 to the n is larger than 5 to the n, and since this is in the denominator, then 1 over 2 plus 5 to the n must be less than 1 over 5 to the n. Now, if I know that this term is less than this term, then it doesn't do me any good unless I can show that the series from this term is actually a convergent series. But actually, it is a convergent series because here r is 1/5. So this is actually a convergent geometric series. And you can easily show that. Just go back and read about geometric series. So this is actually a convergent geometric series, and since all of the terms in my series I started with are less than the terms in this convergent geometric series, then I know that the given series, the one I started with, converges. Okay, so now let's look at this series, 3 over square root of n minus 1. Now, I'm only going from 2 to infinity, and the reason I'm doing that here is because it wouldn't make sense to start at 1, because then you would have 0 in the denominator. So let's go from 2 to infinity. Okay, so if n is greater than or equal to 2, then we can actually show that 3 over the square root of n minus 1 is greater than 1 over the square root of n. Okay, so you can plug values of n and show that in here, but the point is that the term 3 over square root of n minus 1 can be shown to be bigger than the term 1 over square root of n. And you can show that square root of that 1 over square root of n, that's 1 over n to the 1/2, is actually a divergent p series, because p would be a half, and since a half is less than 1, that means this series is divergent. Now, it really doesn't matter that you're starting at 2 here instead of 1, because really the only difference between this series and if you started at 1, the only difference would be, like, if you started at 1, you would get a divergent series, so basically the series goes to infinity. So if you start at 2, you just lose that first term, which is 1. But if you take 1 away from infinity, you still got a divergent value of infinity. So anyway, so this is a divergent P-series, and since all the terms of this series here are greater than the terms in this series, then the given series diverges. Now, another comparison test is called the limit comparison test. And in that test, if you have a series A sub n and a series B sub n, if they're both positive term series, and if the limit of A sub n over B sub n equals a positive number, if it equals some positive number, then either both series converge or both series diverge. So what you need to try to find is a series that you already know whether it converges or diverges, and then hope that it works out the appropriate way for you. Okay? So let's see here. Here's an example here. I have 1 over the cube root of n squared plus 1. Okay, so here's what I'm going to do. Since that's cube root of n squared plus 1, let me use the series that has the term 1 over the cube root of n squared, because that'd be 1 over n to the 2/3 power. And we know by the P-series that 1 over n to the 2/3 power is a divergent series. So now let's do the ratio. Let's take our given series, okay, and let's put it over this series. Now, I probably should have shown that, so let me pause the video here for a second and draw that for you. Okay, so here, remember, this is what I wanted to do. I want to find the limit of A sub n over B sub n. So that would be the limit of 1 over the cube root of n squared plus 1 divided by 1 over the cube root of n squared. Now, if you take this and divide it by this, you're just going to flip the denominator over and multiply. So basically, if you do this division here, you would get the cube root of n squared over the cube root of n squared plus 1. And since these are both cube roots, you could think of it as a single cube root with this quotient inside it. And then we can think of that as just the cube root of the limit. So the cube root of the limit of n squared over n squared plus 1. And of course, on all these limits, n goes to infinity. So the limit of this would be 1. So you would end up with the cube root of 1, which is 1. And so now I've shown that the limit of A sub n over B sub n as n goes to infinity is 1, and that's a number greater than 0. So since I've shown that the limit is a number greater than 0, then either both of the series converge or they both diverge. But since I already know that this P-series diverges, then that tells me that they must both diverge, so the given series must diverge. So now let me clean this up a little bit. Okay, so this one here, I'm going to have 3n squared plus 5n over 2 to the n times n squared plus 1. So this is my given series. So what I can do, I'm going to compare it with this 3n squared over 2 to the n times n squared. And that actually is the same as, because the n squareds can cancel and you get 3 over 2 to the n. Okay. Now, actually, if I do the comparison here, I would actually be taking this series, this term, 3n squared plus 5n over 2 to the n times n squared plus 1, and I'd be dividing it by this term. Well, since I'm dividing by a fraction, I would actually end up inverting and multiplying. So what I showed you down here, if you look down here, you'll see I've taken the first term and then I inverted the second term, and so I get 2 to the n squared over 3n squared, and probably didn't even have to write the n squareds. But then notice that the 2 to the n cancel, and so I end up, if I take the limit of this as n goes to infinity, I end up with 3n squared plus 5n in the numerator, and so there that is. And then in the denominator, I end up with 3 times n squared plus 1, so there that is. Now, you should be able to show now that if you take the limit of this as n goes to infinity, that you should be able to show that this equals 3 over 3, which is 1. And again, 1 is a number greater than 0. So since the limit of a sub n over b sub n is greater than 0, then we know that both of these series either converge or diverge, but actually the 3 over 2 to the n is actually a convergent geometric series. Therefore, the given series that we started with must also converge. Okay, so again, using the limit comparison test showed us that our given series converges. So I'm just going to wrap this up with a few series here. So, and we're going to determine if these series converge or diverge. So the first series is 1 over n factorial. Now if you remember, n factorial just means you just multiply 1 factorial is 1, 2 factorial is 2 times 1, 3 factorial is 3 times 2 times 1, and so forth. So 1 over n factorial would give me the terms 1 plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial, and so forth. All right. So if you were to write out all of these terms, okay, 1 plus this series, and let me write that for you here just a second. So the series 1 plus the series 1 over 2n plus 1 over 2n, where n goes from 1 to infinity. We're adding the 1 in here just so we can get the 1, because if you start at n equal 1, this actually starts at a half. So we have the 1, so that's 1. And then when n is 1, you get a half. When n is 2, you get a fourth. When n is 3, you get an eighth. So I want you to compare term by term here and just look at these. Well, 1 is less than or equal to 1. 1/2 is certainly less than or equal to a half. But 1/4 is, I'm sorry, I'm saying that backwards. The 1 here is less than or equal to 1. 1/2 is less than or equal to a half. Now this is 1/6, and 1/6 is certainly less than or equal to 1/4. This is actually 1/24, and 1/24 is less than or equal to 1/8. So all the terms in my given series are less than or equal to the terms in this convergent geometric series, and so by the direct comparison test, this series must converge. Okay, and then this next one, let's say natural log of n over n to the 3/2. Well, you can actually show that this is less than or equal to n to the 1/4 over n to the 3/2, which is actually 1 over n to the 5/4. So you can show that this series, this term, is less than or equal to this term. And this series, the series actually converges from the p-test. So I should have said the series there, not the term. So the series converges from the p-test. So therefore, this series that we're given must converge, because all the terms in this are less than or equal to the terms in this. Now on the last one, I just did the limit comparison test. So you take the limit of the 2n plus 1 over n squared plus 2n plus 1 over 1 over n, and what you'll end up with is 2n squared plus n over n squared plus 2n plus 1. And if you take the limit of that as n goes to infinity, you'll get 2, which is greater than 0. Now that doesn't mean it converges. It means that the two series must do the same thing. And so since I compared it with the divergent harmonic series, and I got a number greater than 0, then the series that I'm given, that I started with, must also be a divergent series. Okay, so now put those comparison tests in your pocket and hold on to them. And in the next section, we're going to talk about some tests called the ratio and the root tests.